Hello, Wajid. Can you hear me? Hello.
Hello?
Okay, so I was telling you about this one. Like for the mass spectrometry, previously when we did mass spectrometry, I've told you that this is the first step. This is called inlet, okay, through which we add the sample. Okay, sample can be any compound. Basically, in mass spectrometry, we are visualizing or we are detecting the organic molecules.
Okay.
Okay, organic molecules can be like methane, ethane, propane, butane, pentane, any compound. Propyl, amine, nitrile, whatever it is. Whichever component we are taking as a sample, we just put it into the mass spectrometer. Okay. And in the second step, like this is the first stage where we say is the inlet present. And then there's the second stage, which where the beam of electrons is present. Okay. We also call this second step as the ionization chamber. Okay. Whichever sample we just introduced into the spectrometer, this kind of high energy beam electrons, they're falling, and the sample, it gets ionized there. Like whichever like below we have given the example of this butane. Okay, so this electron, this plus electron that I've shown you,
Yeah.
this electron, it's actually the beam of electrons that is present at the second step. I've told you that this is the ionization chamber where the high energy beam of electrons are falling. So what they do with the sample, those high energy or high speed electrons, they will knock out the electron of the sample.
All
Okay.
right.
So this beam of electron, this will strike with the sample and it will knock out its electrons. That's why here it is one electron and in this side we have the two electrons. Okay. So this high energy beam of electron will strike with the sample and it will knock out its electron and the sample gets ionized. Okay.
Okay.
And at the end, like the sample, the ionized sample or the ions, they will then deflected by the magnetic field and are deflected at different angles, and then they are detected by the detector. Like at the end stage, we have the detector that is installed, and that detector is then fitted with a computer, and on the screen you will see the graphs. Okay, they will not give you
Okay.
that this is ethanol, this is methanol, this is alcohol. No, the computer will give you the data in the form of graph where we will see or observe the peaks.
Hmm.
Okay, and we
Okay.
call this graph as spectrum. So the 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 graph that is obtained as a result of mass spectrometry is spectrum, and on the spectrum you will observe different peaks. Okay,
Okay.
is this clear up to this point, up to the point where
Yeah, it's
we
clear
are?
to this point.
Okay, so this is this is the sample that gets ionized, is deflected by the magnetic field, and it is deflected at different angles, and this detector is then attached to the computer, and computer is giving us the graph, and this graph is known as the spectrum. And this spectrum, like for visualizing the spectrum or to interpret the data from the spectrum, you must know this first thing, which is like the peak, which is furthest, okay, is having the most M to Z ratio. Like it's obvious, like when you move towards right, the value is getting increased. Okay, so the peak, like when you have the spectrum in front of you, the peak which is furthest and the one which has the most M over Z value is called the molecular ion peak. This is the molecular ion peak. Okay, maybe you'll see some peaks over here, some peaks here, some peaks here, but the one which is furthest and has the most M over Z value, That is actually the molecular ion peak. Is it clear up to this point about the molecular ion peak?
Yep.
Hmm?
Yep.
You can ask me questions in between if you.
So molecular ion peak, this means it's the full molecule, but what about these smaller peaks? What do these smaller peaks mean?
These are the fragments. We will discuss them later on. But firstly, you must know what is molecular ion peak. Okay, the one which has the most m over z value, this peak is called the molecular ion peak. And actually, this is formed by the losing of electron from the molecule, organic molecule, whichever molecule we are using as a sample. When it loses its electron, okay, like this is the sample, CH3, okay? So it just has lost its electron, this one. So this peak is actually referring to this one, ion, not the molecule. That's why we are saying it's molecular ion peak. Whichever molecule we are using in the sample, when it gets ionized, the peak it is showing is the molecular ion peak. Is it clear
Okay.
now?
Yes, it's clear now.
Okay. So you must remember that it's actually the one which is having the greatest m over z value. And this is formed as a result of losing an electron in the mass spectrometer. Okay.
Okay.
Okay. The one which is having most m over z value and the one which is formed by the losing of electron in the mass spectrometer. And this is the equation CH4H10. And this electron, it strikes to this butane and it will kick out or knock out its electron. And this is the ion that it is forming. And the peak, which is being shown by a, like the peak which is observed in the spectrum with the greatest m over z value, we call this as molecular ion peak. So this equation, you can say that this is the molecular ion peak of butane.
Okay.
Okay. Okay, so along with molecular ion peak, we are also getting some small peaks as well. Okay, and one peak is like very short peak, and it is just to the right of the molecular ion peak. And we are also naming, like previously, we already did this about we have one M peak, and along with it, there's like a short peak. We call this as M plus one peak.
Okay.
Okay, so it's
What's on this?
actually
What's M and M plus one?
M is whichever molecule we have in the sample. When it gets ionized, that peak is actually the molecular ion peak. And this M over M plus 1 is actually related to that molecule may have the isotopes. Okay. So
Okay.
the naturally occurring isotope of carbon, or like most of the times in organic molecules, the main skeletal or main backbone of a compound is carbon. Okay. So this small peak is actually the naturally occurring isotope of carbon.
Okay.
Okay. Like for all the organic compounds, if you see the main component is carbon, or you can say for all the organic compounds, the backbone is carbon. Okay, so within the spectrum, the small peaks, which is just right to the molecular ion peak, it is actually due to the naturally occurring isotopes of carbon. Okay, like basically carbon exists in this form, C12. Okay, but we have another isotope of carbon as well, C13, and C14 also, but most of the time it's C13. Okay. So if you see, 99% of carbon actually exists in C12 form. And the remaining 1% is actually due to C13. C14 is radioactive. Okay. However, C14 also occurs naturally in organic compounds, but it is radioactive. So We are not discussing it most of the time. We call this as radioactive or radiocarbon dating.
Can you just explain what's M1 and M plus one M again?
Sure. Like whichever compound that we are using as a sample in mass spectrometry, okay, whichever sample. I've just told you that for mass spectrometry, basically we are detecting the mass to charge ratio for the organic molecules. And this is how the organic molecules get analyzed and determined. Okay. Mass spectrometry is basically a technique in which we are detecting the organic molecules. Which of the organic components are present within a sample? Like for example, we have any fruit. How many content of ethanol is present? How many methanol is present? Actually, we are detecting this by mass spectrometry. Okay, like we are detecting which organic substances are present within. Like we have the biofuels, we have the bio organic molecules also, just like amino acids, proteins, carbohydrates, lipids, all these,
Hmm?
they are the biomolecules.
The ones with carbon?
Yes,
Hmm.
all of these, they are the organic molecules, they are the biomolecules, they are the biofuels, along with the other ones, the ones that are um, used as a fuels. They're also hydrocarbons. Okay, petrochemicals, they are also the organic molecules. Along with this, we have the biomolecules, bioorganic molecules like proteins, lipids, carbohydrates, fats, enzymes, all these. They are the biomolecules. So this mass spectrometry, this is actually the technique which is used to detect the presence of those organic molecules within a substance. Okay, like how much content of that is present within a substance. So basically, this technique is used for that purpose. Is it clear?
Yeah.
Okay, so this is mass spectrometry by which we detect the substances, the elements, the components that are present within a sample. And how it works, this is how it looks like we have a inlet in which we add the sample. Then we have the ionization chamber where the high beam electrons will knock out the electron of the sample and the sample gets ionized. In the fourth step, there's magnetic field that is present and it will deflect the sample. The lighter samples, they will be deflected more, and the heavier samples, they are deflected less. And this is how we get the data for the components that are present within the sample. Like if we have the lighter components that are present or we have the heavier components that are present. So the mass spectrometer or the detector or the computer, they're not giving the data in the form like we have the ethanol is present, methanol is present, alcohol is present, proteins are present. No, actually it is giving us the data in the form of graph. Okay, like you will see so many peaks and lines that are like analyzed by you, and you have to detect which of the components that are present within this substance on the basis of their peaks. It's kind of the
Okay.
language for computer, but you have to interpret it on your own. Computer is giving you the data that this are the peaks, and you have to visualize that which of the components are present within the substance. Okay, so this detector, which is connected to the computer, and computer which gives you the graph in the form of spectrum, the spectrum you have to analyze it on your own, that which is the molecular peak, which is the molecular ion peak. Okay, so this is how you will get the spectrum. Like on y-axis, you will have the relative abundances, and on x-axis, we have the mass to charge ratio, m over z value. So from that, first of all, we will observe like which peak is the furthest. The one which is
Yeah.
having the greatest mass to charge ratio, it is actually the molecular ion peak. Molecular ion peak means whichever molecule we have the sample, it gets ionized, and the peak we are getting, that's why we are calling this as molecular ion peak. Like molecule means whichever molecule is in the sample, And ion means it gets ionized. And the peak that we are observing it in the form of mountain, we call this as peak. So that's why it is molecular ion peak.
Okay.
Okay. So for this, we have the sample which is butane. Okay, we just added it into the sample inlet. And this beam of electrons, it will knock out the electron of butane, and butane gets ionized. The C4H10 positive is formed. Along with it, the electrons are released. They will remain within the ionization chamber. Okay. And this is the sample that is getting ionized. And on the spectrum, if you observe, it is having the most M over Z value. This is the peak of this sample, which we call molecular ion peak.
Okay.
And right beside this molecular ion peak, you will observe a small peak, which is actually known as M+1 peak. Okay. Like the main backbone of organic molecules is carbon. And carbon actually
Yeah.
exists in its three isotopic forms. Okay. C12,
Okay.
C13, and C14. Okay. The 99% of carbon actually exists in the form of C12. Only
Mm-hmm.
1% exists in the form of C13. And C14 is also a form in which the carbon exists, but this is a radioactive isotope. And we only considered this C14 during radiocarbon dating. So most of the times we are not considering it. Okay, so we are only dealing with these two. That's why whichever compound which is being observed as a molecular ion peak, along with it, this peak is shown up, C13 peak, which is M+1 peak. Is it clear?
Okay.
Okay. All organic compounds, they have the carbon in them. All. The basic structural entity in them is carbon. Okay. So whenever, whichever compound it is it protein, lipids, ethanol, methanol, propane, butane, that gets ionized, the sharp peak or the big peak or the one which is having the greatest M over Z value is that molecular ion peak. And right beside that molecular ion peak, you'll see a small peak. We name this as M+1 peak. That is actually the peak
The
of,
smaller peaks are called M+1 peaks.
yes, they're not the peaks. It's the only one peak, which is right beside the molecular ion peak. We call that as M+1 peak.
The one that is right beside the molecular peak.
Yes, like we have so many of the small peaks that are present within the spectrum. We are not calling all of them as M+1 peaks. The only one which is present right beside the molecular ion peak is called the M+1 peak. Is it clear now?
All right.
And the one which is having the smaller M over Z values, like the one that are lying over here or here or here, they are the other compounds. And we call them as the fragment peaks. Okay. Like the one that has the smaller M over Z values, they are result from fragmentation.
Okay.
Okay, the peaks that are having smaller M over Z values, they result from fragmentation in the mass spectrometer. Like there is kind of rearrangement reaction, and there may be the loss of more than one electron. Like the molecular ion peak, we say that this is the peak which is uh, being shown by a sample when it gets ionized, and this sharp peak, and it has the greatest M over Z value. Okay, but the smaller peaks, they are actually as a result of fragmentation, like they may have lost more than one electron. There may
So
be some
what?
side reactions that
Why
will.
is there m plus one peaks then? What's the m plus one peak?
Most
Like,
of the time, it is of no use, okay? It's basically the isotope of carbon's peak. It's a very
okay,
small
fine.
peak.
The one that is directly next to the molecular ion peak.
Yes, the one which is directly next to the molecular ion peak is the M plus 1 peak. It's actually the peak of C13. Okay, that's why it is showing in a small line. Okay,
Okay.
and these other small peaks, the one that I've shown you in red, they are actually the peaks with smaller M over Z values. Like if you see, it is having maybe 38, this is having 20, this is having 14, maybe this one. These peaks, okay, they are having lesser or smaller M over Z values. And they are happening due to fragmentation in the mass spectrometer. Okay, like there may be the rearrangement reaction, there may be the loss of one or more electrons. Okay, so basically, like it is, they are also giving us the idea that which of the functional groups are present within the sample.
Okay.
Or like when we were discussing about bond enthalpies, like within the organic compound, this is the compound. How much CH bonds are present, how much CC bonds are present. So how much CC bond is present, how much CH bond, they are also showing their own peaks. Okay, so the breaking of this carbon to hydrogen bond, it can occur. And
So there's
those,
just different break, like these compounds are broken, and then these peaks show the broken parts.
yes, that's why we are calling it as fragmentation.
It's a result of fragmentation.
Okay, like it is related to breaking of carbon-carbon bonds, breaking of carbon to hydrogen bonds. Okay, so like most of the times when we are breaking these carbon to carbon bonds, uh, two species are formed. Maybe another positive ion is formed, or maybe a neutral species formed, which we call radical, like the one that we were discussing about radical mechanism. So maybe the ion is formed or a radical is formed during fragmentation. Okay, like for example, we have the ethane molecule. Okay,
Okay.
what is the formula of ethane?
C2H6.
Yes, C2H6. Like we can also write it as CH3CH3. Okay, so this is ethane. So there's like a bond between carbon to carbon. So if this bond breaks, what happens? Like we call this as fragmentation. Okay, the carbon-carbon bond breaks, and the molecular ion of ethane, it can fragment to form methyl cation and methyl radical, which is like this can form along with this is formed. So we can also represent it by a dot. So we say that this is methyl ion and this is methyl radical. As a result of fragmentation, the molecular ion of ethane can fragment to form methyl cation and methyl radical. Okay, so this is actually the fragmentation of ethane. Are you getting this, Wajid?
Yep.
This is the fragmentation of ethane. Okay, so when the fragmentation of ethane happens, it will result in the formation of methyl cation and methyl radical. Like within within that peak, within the spectrum, you will observe, like, actually we have the sample as methane, CH3. We just put it in the spectrometer and it gets ionized. This is the methyl ion. Okay, so the M peak, you will observe it of methyl ion. Sorry, no, ethane molecular ion, ethane. The M peak will be of this. Okay, after its fragmentation happens, and it will give us the methyl ion radical as well as methyl ion as well as methyl radical. Are you getting this, Wajid? Like within the
Yeah.
sample, within the mass spectrometer, we have put ethane as sample. This is ethane, that was the sample. In ionization chamber, it gets ionized and it has converted into this one.
Okay.
Molecular ion of ethane is formed and its peak will be M. Okay, the molecular ion of methane, sorry, ethane, molecular ion peak of ethane is formed. And after its fragmentation, the molecular ion of ethane will fragment to form methyl cation and methyl radical. Is it clear up to this
Okay.
point? Any questions up to this point, Vajal?
Yep.
Hmm?
Uh, no. Actually, I got it. I got it.
Okay, so this ethane was sample. It was put into the mass spectrometer. In the ionization chamber, it gets ionized, and we get the molecular ion of ethane, the one which will be observed on the mass spectrometer as the very sharp peak with having most greatest value of M over Z. Okay, so this molecular ion of ethane, it will then fragment to form methyl cation and methyl radical. Okay, so if you see this ethane molecule, it's actually symmetrical. Why we are calling ethane as symmetrical? Why, Vajit? Why ethane is
Hmm.
called as symmetrical?
Because both sides are they have the same arrangement.
Yes, it has the
So
equal number of ethyl groups on both sides. Okay, so this ethane molecule is symmetrical, and there's only one carbon to carbon bond in ethane. This this one bond, the one that we have broken up. Okay, so you can observe, or you can say that this any of the carbon in ethane, CH3, CH2, we have, can become radical or can become positive ion. Okay, so it can be this one or it can be this one. Okay, like both the products are similar. If you see, are you getting any difference in these two? Wajid,
the hell.
are you getting any difference in these two? Like molecular ion of ethane, it can form molecular, like it can form radical with this carbon or that carbon, or ion with this carbon or that carbon. Why? Just because it's symmetrical. Okay, this ethane molecule is symmetrical, and there's only one carbon to carbon bond, this bond. Okay, so when it breaks up, this carbon will become the positive ion, like this methyl group can form the positive ion, or this methyl can form the radical, or this can form the cation, or this can form the radical. Like actually, the thing is that they both are similar. So any carbon can take up the ion, or any carbon can take up the radical. Why? Just because they are symmetrical. They both are identical. Okay. So this
So what
bond,
happens if they're symmetrical though? Like,
when they're asymmetrical, the bond breakage is kind of different. But when they are symmetrical, or the products, they are identical, then the spectrum does not depend on how the bond is breaking. Okay, like on the spectrum, we have the data collected for all of the functional groups. Like most of the times, this methyl group is forming molecular ion peak at 15. Okay, maybe you
okay.
are given the table. The M over Z value for methyl cation is 15. So whenever you'll observe the 15, like the peak at 15, you'll get the idea that maybe the methyl is present here. Okay. So as the products, they are identical. So the spectrum is not depending on how the bond is breaking. And you'll always observe the peak at M over Z is equals to 15. Okay.
Okay. CH2, okay, fine.
So most
Just
of the,
oh, one second, I'll be right back.
okay. So we were discussing about this one.
Yeah.
If this compound is symmetrical, you're getting like this kind of same radical and same cation that is being formed. Okay, like we are not in the contents of your book, we are not getting any of the asymmetrical components. Okay, all are symmetrical. But within the symmetrical, it's not like always the ethane we are using. For example, if we have the propane, okay, like the chain has been prolonged. So now there's not a single carbon to carbon bond, but there's kind of another carbon to carbon bond as well. Okay, like if for this one, for the ethane molecule, you will observe the peak at 15. Okay, that is actually every time for methyl ion. Okay, you will observe the molecular ion peak. Molecular ion peak is actually related to the molecule which is in the sample. Okay, when it gets ionized. So this is the molecule ethane. This is the molecular ion peak of ethane as 15, or methyl cation as 15. So you have to keep in your mind that this methyl cation will always appear on the spectrum as 15. So when you see a peak at 15, you'll get the idea that methyl cation is present. Okay. Like for example, if we have the molecule as propane. Okay, what is the formula of propane?
Formula of propane is C3H8.
Yeah, or we can write it as CH3, CH2, CH3. Okay. So for this one, for propane, you'll see that we have two carbon to carbon bonds. One with this, one with this. Okay. Two C bonds, CC bonds. So we call these as terminal carbons. These are the terminal carbons, and this is the central carbon. Okay, the carbons that are present at the end of the chain, they are the terminal carbons, and the carbon that is present at the center, we call that as the central carbon. Okay, So for the propene molecules, we have two carbon bonds, and they are equivalent. Okay, so one is between the central carbon, and the other is between the two terminal carbon atoms. So if you see the fragmentation of this um, propane molecular ion, basically we have this CH3, CH2, CH3 propane molecular ion, and its fragment will be like maybe one is this fragment in which we have the methyl group and the ethyl group. Okay, like it will fragment up into two parts, CH3 plus CH2, CH3, and maybe this will be considered as a fragment, and maybe this fragment goes to this one, and this, there are two possibilities. Other is like CH3 radical plus CH2, CH3 ion. Okay. So on the spectrum, it's always that one of the peak you will observe is of the methyl. Okay. And another peak for this ethyl ion. Okay. So on the spectrum, you will observe that one peak is at 15 and other peak is at 29. So this 29 peak, you will be given the data table in which there will be like peak CH2, CH3 is equals to 29. So you'll observe that there's ethyl ion that is formed as well as methyl ion. 15 peak is referring to ethyl and 29 peak is 15 is referring to methyl CH3 positive, and this 29 is referring to ethyl ion, which is CH2 CH3 positive. Okay.
Okay.
So basically these detectors, they are, sorry, these radicals, they are not detected. They are not showing any peak. Otherwise, there will be a lot of noise within the spectrum. Noise means the unwanted peaks that are shown in. But this spectrum that you will get in, there is no peaks related to the radicals. The only peaks that are shown up are the ion peaks, molecular ion peaks. Okay.
Okay.
So from the molecular ion peaks, you will interpret the data like you'll get the idea that if peak is at 15, it means methyl is present. If it is at 29, it's ethyl is present. If it is at 43, it means propyl. If it is at 58, it's butyl. Okay, like if have you have the book in your laptop? You can just share the screen, and I'll show you the table from the book. You can just, now you can share the screen, Roger. Just zoom in.
Yeah.
Yeah, this is the table if you see. This 15 is referring to methyl cation. Okay. 29
Yeah.
is referring to ethyl. Then 43 is related to propyl. And 58 is related to butyl. So if you see this one, this is referring to methyl CH3 positive. Okay. 29 means there's ethyl present. Here we have the propyl. 58 butyl. Is it clear now?
Yeah.
This is molecular ion peak. This is the most abundant peak over here. So all these peaks, they are actually by the ions. Okay, we are that's why we are calling them as the molecular ions peak and peaks, not the radical. These you can say are suppressed. These are not shown up, the radicals. Okay, most of the time, the spectrum that we are given, there is large number of peaks that are actually not of any use. Okay, if you scroll down, Majid.
Yeah, okay.
Hmm.
Yeah.
Yeah, just read out this whole information. Read this, Majid.
So which one?
The possible information, this one.
So possible. Okay, here's information you could be given in the exam questions. The complete mass spectrum. The disadvantage of this possible large number of peaks is cannot be used to work out the structure and would be distracting. Another possibility is a mass spectrum, but with only the MZ values of the useful peaks marked on the spectrum. A simplified mass spectrum, only peaks that will help you out a structure, work out a structure, and a list of MZ values, useful peaks. With practice, you'll be able to work out the structure of an organic compound.
So you always have to take out this idea that the M over Z values, they are actually giving the idea of M peak, molecular ion peak. Okay, if if that is small or large, that actually indicates its abundance, its relative abundance, how much the substance is present. So you don't have to like confuse with this that why this peak is small or why it is very large. When you're going towards right, it's actually the M over Z is increasing. Okay. So at that point, whichever, like within the data, you'll be given that if ethyl is present, you'll have to mark it at the 15 point. Like if you'll observe the peak at 15, it means ethyl is present always. Okay, like they are actually the detected values. So you are just interpreting it from the spectrum. There are so many other peaks as well within the spectrum. So you're not considering them. You're not um, giving any importance to any of the peak other than which is in the compound. Like the one that is in the compound, you're just marking those on the spectrum. Okay, the next you have to read this one as well.
So the traditional way to present a mass spectrum is to label the vertical axis as the relative intensity and the horizontal from to M mass to charge ratio with no units. The horizontal axis usually but not necessarily starts from zero. It continues to just beyond the molecular ion peak.
Okay, so the one which is the largest, like the one which is having the most height, we call that as the base peak. Okay, the peak with greatest abundance is the base peak, and the peaks that are formed from the loss of electrons, we call those as molecular ion peaks. Like whichever molecule we have in the sample, when it has lost its electron, then it becomes M positive. And that's actually known as molecular ion peak. Okay. And fragmentation is this molecule, whichever molecule we have, when it breaks up, like I've told you about ethane and propane. Ethane has one CC bonds and propane has three. Okay, so it is going to form ethyl, and it is propane is actually forming Sorry, this is only forming methyl cation. And when propane is breaking up, it can form methyl as well as ethyl ions. Methyl ion as well as ethyl ion. So you will see two types of peaks within the spectrum. For ethane, for ethane, you will see only one type of peak in the spectrum. Okay, it actually depends how long the chain is. And then you will get the idea that how many peaks you will get out of it. Okay, next page.
Next page. Deducing structures from spectrum.
Fragmentation in other organic compounds.
So far, we have looked into mass spectra of alkanes. Now let's look at other compounds like those containing oxygen. In this topic, we'll look at two examples of simplified mass spectra and see how they can be used to work out the structures. Oxygen is present in many organic compounds, so you need to be familiar with the MZ values. You may also come across compounds containing amines and halogenoalkanes.
Okay,
So
this
these
is
are
the
the
table.
possible.
This is the possible MOZ values of different functional groups. Okay, so 15 is always for methyl. Then you must know that 17 is for alcohol. Carbonyl carbon 28. Okay, this one. Like where the carbonyl carbon is present, can you tell me um, any compounds in which the carbon?
Carbonyl carbon.
Hmm. What is carbonyl carbon, Bajar?
So basically, a ketone.
Show me the structure of ketone on the screen.
Yes. So
Is it all? Is that all?
yeah, that's a ketone, right?
Where's the carbonyl carbon?
Oh wait, never mind. It's double bonded to oxygen. Wait.
Yes. Okay. So this carbonyl carbon, whichever carbonyl it is always having the peak at 28.
Just 1 second, I'll be right back.
We were discussing about this one, about carbonyl carbon. Okay. So every time, whenever the carbonyl carbon is present, it will show up its peak at 28.
Yeah.
Okay. But you must have to keep this thing in mind that if carbonyl carbon has the peak at 28. Okay, 28. But if it is aldehyde, then it is at 29, CHO, which means at one side it's hydrogen. Are you getting this? Like the carbonyl carbon is showing its peak at 28. But when the aldehyde is present, then it is showing at 29. Aldehyde may be formaldehyde or acetaldehyde. Okay, this is acetaldehyde. It is showing peak at 43. Acetaldehyde. Are you getting this, Wajid? CHO is aldehyde and CH3CO is acetaldehyde. Okay. And then alcohol is showing peak at this 45. And ethanol, methanol is showing at this one. This is for ethanol. Like you will interpret, you're already given the table. You don't have to confuse it with like which value has, like you are just interpreting it. Like if you have this one, this is scroll towards the interpretation. With example, this blue part, scroll towards that side margin. And also read out this learning tip, Wajid, this below table. Wajid, this one, read it.
It is sometimes worth comparing the MZ values of the fragment ions with that of the molecular ion. Difference is that two indicates what has been lost during fragmentation. For example, the molecular ion peak is at MZ60. There's a fragmentation ion with MZ45. The difference is 15, which suggests the loss of CH3.
Okay, what are you getting from these lines? Wajid, what happened?
Hmm?
What are you getting from these lines? Are you getting nothing?
I'm getting something.
Okay, tell me whatever you have got.
So what I got is that we have to compare the MZ values of fragmentation ions with the molecular ion, which indicates what was lost during fragmentation.
So what does this mean? Like if we have the molecular ion at 60 and then we have the fragment at 45, so how it gets the idea that there was CH3 present? There was methyl group present over there. How you get this idea? Like, how are you getting this idea that if we have the uh, molecular peak at 60 and its fragment at 45, so it must have the methyl group in it? Okay, so basically it is like this 60 means it is kind of long chain molecule of carbon, okay? Like 57, it's this one, methane, ethane, propane, butane. It's butane for 57, okay? So 60 means it is kind of butane or pentane. And its M over Z values is shown at 45, means this 60 has lost 15. So 60 minus 15 is 45, okay? So now it means that actually 15 has taken out from it. So 15 means 15 refers to which group? Like whenever we have the 15 on the spectrum, it means it is referring to which functional group, Wajid? M over Z is equals to 15
Yep.
means what? I'm
Methyl
asking you.
group.
Yes,
Methyl
methyl.
group.
Yes, methyl group. So it means one of the methyl group has been lost. And that's why we are showing or we are observing the peak at 45. One of the methyl group has been lost from it. Okay.
Okay.
15 lost means one of the methyl group is lost and now it is showing the peak at 45. Let's go towards this blue part, the interpretation part, the word
Yeah.
examples. Delete all of this. Okay. So if you see, we have two compounds, A, B, and they have the molecular formula of this, CH3H6O. Okay. This is their mass spectra. And now we have to deduce that which component it is. So this component, firstly, when it goes to the mass spectrometer, it gets ionized and we will get C6H6O positive.
Okay.
Okay. So the furthest peak is this one. Like firstly, we will observe the peak which is further or furthest. So this peak is furthest and its value is 58. Okay.
Okay.
So it has one of the peak at 15, this one, which means 15 means 15 m over z is equals to 15 means which is present, which functional group is present. Wajid, 15 means
Hmm?
which functional group is
Methyl
present?
group.
Methyl group. So this is component A, this is component B. So they both have the methyl groups in common. Okay.
Okay.
Both A and B, they have the peaks at m over z into 15, which is actually due to the methyl ion, CH3 positive
Hmm.
ion. This is also CH3 positive. Okay. And then we have this peak for A, we have one peak at 29. And for B, we have no peak at 29. Okay. So at 29, see the table. At 29, which functional group is present? 29 peak is, go towards this table, Vajid.
The 29 peak is due to wait. Just wait.
You can just scroll sideways and you'll get.
Oh, it's OH.
No, 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 no.
No, it's a CHO.
No, this one.
Which one?
This one, 29 is this. CH3, CH2 positive or CHO positive.
That's a yeah, CHO positive. Yeah.
So this CH 29 is due to CH3, CH2 positive, which is or CHO positive. Okay. So what do you think? Which component it is? This one, A component. If you add up CH3, CH. Two compounds have the molecular formula C2C3H6O. Okay, this is the formula that they have given. This is the results that we have
Yeah.
interpreted. That one is methyl and one is CH3, CH2, or this one. So from
Yeah.
this interpretation, uh, the structure of the compound, it can be CH3, like 3 carbons. So it can be CH3, CH2, CHO. So it's an aldehyde, which is, you can say, methane, ethane. So it's an methane, ethane, propane. So it's a propanol. So this is how you interpreted that structure A is a propanol. Okay. For B, if you see, we have the other peak at 43. One at 15, one at 43. Okay. So if you see, what is for 43? 43, which functional group is present?
43.
Hmm.
For 43.
It's CH3, CH2, CH2 positive. 43 is CH3, CH2, CH2 positive. Or it can be CH3, CH3 positive. Okay. So the compound that they have given is having 3 carbons. So one carbon is this. So it can be this one or that one. and we have one oxygen, okay, which has the mass of 16. So the possibility is that it is forming CO, CH3CO. So it can be ketone. Like you see, for the compound that they have given is having oxygen in it. Okay. And for 43, it is maybe this one or this one. Okay. So both of them, they don't have oxygen, but this one has this hydrogen in it. So we can say that the possibility is this one, COCH3. It's a ketone. Okay. Like we have to deduce like how we got these compounds, the ketone for B and aldehyde for A. It's like for this A compound, if you see the M over Z value is like the most highest value is this one. Like the base peak is 29. The base
Mm,
peak for A is at 29. Okay.
okay.
Its M over Z value is 29. And at 29, we have the functional group as aldehyde. Okay. So
Okay.
the 15, which is the methyl group peak, we will say that the compound is CH3CH2CHO. Okay. So CH3CH2CHO. This is the molecular ion we have. So we just do its fragmentation. Okay, like if we do its fragmentation, that like the carbon, this bond can be
Okay.
broken up. So it can be like this CH3 CH2 positive, CH3 CH2 positive, and along with this we have CHO radical, or we can have CH3 CH2 radical. Along with this we have CHO as positive ion that is formed. Okay, so this is how we do the fragmentation. This is called fragmentation. Okay, once we
Okay.
have detected the compound, then we do its fragmentation. So these are the possible fragments. Like one fragment, one peak is for this one,
Mhm.
ethyl, and other is for methyl or aldehyde. Like you are doing the practice for both of them, and then you are analyzing it more clearly. Like you're getting the clear idea. Firstly, if you
Okay, but like, okay, if we're given this graph, then how will we know which one is which? Like, which of these is which?
like from the 15, you just got the idea that this is the methyl. Okay. From this, you said that it's 29. So the
Yeah.
29 is actually referring to which peak? You will then check it from this table. It's CHO, it's aldehyde, 29. Okay, it's actually
All
referring to
right.
both of them. Like when we have both, we actually are selecting it from the compound that they have given us. The compound that they have given us is C3H6O. This is the molecular formula. They
All
both
right.
have the same formula, C3, three carbons and one oxygen. Both compounds A and B, they both are having the same formula, C3H6O. And then we are getting peak. Both of them, we are getting peak at 15. Okay, one has smaller peak, one has larger peak. You don't have to confuse it with this. 15 means it's methyl group. You're not going to measure it like how long it is, how short it is. 15 means methyl, always. Okay, 29 means aldehyde or ethyl.
Okay.
Okay, so from aldehyde or ethyl, then we have to take idea that which peak it is. Like for the compound that they have given is having one oxygen in it. So obviously it cannot be ethyl. It should be an aldehyde. That's why we have deduced that it is an aldehyde for compound A. Are you getting it now, Ajit?
Okay. Yeah.
For that, for that reason, we just have observed that it's this compound CH3, CH2, CHO. Why? Just because it has three carbons. So now this compound has three carbons. It has one oxygen. So for CH3, CH2, there's no oxygen. No oxygen. But the compound that we have is having oxygen. So then it must be this one, aldehyde, not this one. That's why we are saying that it is CH3, CH2, CHO. That's how we have interpret this first graph. Go on towards the first graph, Vajit.
Yeah.
Scroll up. Okay,
Mhm.
now listen to me carefully. This
Okay.
graph, if you see, the first value is lying at 15 for compound A. This is compound C3860, the formula that they have given us for both of the compounds, A and B. These are their spectrums. Okay. Both of them, compound A and compound B, both of them, they have this similarity that they are having the peaks at 15. This one is having 15, peak at 15. This one is having peak at 15. Okay, both of them are having peaks at 15, which means they both have the methyl groups in them. Is it clear up to this point? Hmm?
Mhm.
Is it clear up to this point, Vajit?
Yes, it's clear to this point.
Okay, so the compound is C3H6. Compound A and B, we have the spectrums of both of them. And from that, we just have analyzed that both are getting peaks at 15, which means they both have the methyl groups in them. The compound A has the other peak at 29. This is 29, okay? 29 means it can be CH3, CH2, ethyl group, or it can be an aldehyde group within the compound. Okay, so the compound that we have is having three carbons and one oxygen. Three carbons and one oxygen.
And one oxygen, yeah.
If we use this 29 value for this compound, sorry, this is not O, this is CHO, CH, this is CH2. Okay, they are saying that 29 peak is both for ethyl as well as aldehyde. Okay, the compound that we are given is C3860, which means it has three carbons and one oxygen. If we are considering this compound and we make that our compound is this CH3, CH2, and this CH3, so it will make it wrong. Why? Just because the compound that we are given is having three carbons, it has having three carbons, but one oxygen also. This is having no oxygen. So this is wrong. It We will select this one. It's an aldehyde. So that's why CH3, three carbons, that's why we added another alkyl group CH2, CHO. So now it's right. Why? Just because now it is making the molecular formula as C3H6O. Now it's the right one. So this is how we are interpreting it.
Got it.
Okay. For the other one, if you see, one is at 15, other as is at 40,
Mm-hmm.
If you see the next graph, this is at 43.
Yeah.
Okay, one is at 15, other is at 43. For 43, there are three possibilities. Okay, they are saying that it can be CH3, CH2, CH2.
But wait, hold on. 12 times 3 plus 6 plus 16. Yeah, it's
They are saying that these are the three possibilities for 43.
yeah.
Okay, so we have the methyl group. If we are considering this one, it has no oxygen. So we cannot consider it this because its molecular formula for both of these compounds is C3H6O. It is having no oxygen. So this is not right. This is also not to be considered. We will consider this one, CH3CO, for this 43 value. Okay. And our compound will be like 3 carbons. So 1 carbon from this methyl group. So our functional group will be like the compound that we are detecting will be CH3COCH3, a ketone. That's how we analyzed it from this one. That this is aldehyde and this is aldehyde and the below one is ketone. This is ketone and this is aldehyde. This is propanol and this is ketone. Is it clear now? Or are you
Yeah.
still confused at any point, Majid? You can just ask me
Fair enough.
about these two graphs that we have interpreted so far. Are you
I got
quiet?
it.
Are you sure?
Yeah, I'm sure it's like all I need to do is just figure out like which what's the formula for these peaks.
You will be given the table in which you will be given these values. Like if you see in the previous page, there's a table in which they have
Yeah.
given, like if the two compounds are lying in the same region, which is like if you go
Yeah.
towards the table, Wajid.
Okay.
Like if you see, like if we have more than if we have only one compound within that one region, it's simple. Like for 15, you are always known that it is methyl group. When we are like the error comes in when we have more than one functional group is lying in the same region. Like M over Z value of 29 is for both. It is for ethyl as it's for aldehyde. So then we will interpret that which compound we have, and from that we will analyze that which functional group we are taking in the peak. Okay, is this clear now?
Yeah.
So how much time has passed?
1 hour and 30, 40 minutes.
I'm waiting for you from 10, which means 2 hours. And also, if you see, go towards the page. Wajid, just go towards page 289. 289.
8 to 9. Okay, fine.
Okay, so
Okay.
these are the practice questions that you have to do. This question 8, the spectrums that they have given. Question 8, question 10, they are all related to this one. We're going to be finding the substances, like which compound it is. Okay, so this is how the questions come for these type of spectrums. Like from the spectrum, you have to analyze which compound it is. So basically, for these identifications, you will be given the table. From the table, you are analyzing that which functional groups are lying within the spectrum. Is it the aldehyde? Is it the ketone? Is it the propane? It is the like whatever it is. Okay. So this is how you will um, analyze the spectrum, and then you will get the idea that which compound is actually present within the sample.
Okay.
Okay. So then we will move on towards the IR. Like we just have completed this whole mass spectrometry. We're going to read all the things from the book as well as like from the other sources related
Okay.
to your course contents, and then making questions out of it. Like uh, whichever point is confusing for you, you can just ask me the questions related to it. That this point is not still clear and related to
All
mass
right.
spectrometry. And then we will discuss that in our class. For the next class, we'll do this IR, infrared spectrometry, spectroscopy. It's not spectrometry, it's spectroscopy. There's a difference between spectroscopy and spectrometry, okay?
Okay.
So anything else, Rajat? Any questions?
No, no, I'm clear now.
Are you sure?
Yes, I'm sure.
And what about the next class? Are we doing it for tomorrow or for now in the evening?
We're gonna do it tomorrow.
Okay. Okay. See you tomorrow then, Rajat.
See you tomorrow, Nafis.
Allah Hafiz.